Can you see me as well? Okay. Thank you for the invitation to give this seminar. Sadly, most of the people are actually on Zoom today, but that's okay. I hope you'll enjoy the seminar anyway. So I will talk about some work that's been in progress over several years, and it's at the interface of several different topics. As you see in my title, I will talk about the theory of resurgence and how this allows us to decode non-perturbative information from the large order behavior of perturbative expansions in quantum field and string theories in general. And then how this applied to the context of topological string theory, and in particular, from the perspective of the topological string spectral theory correspondence, allows us to discover a connection, a novel connection to analytic number theory. So let me enter into the topic and start with some motivations. In general, having exact definitions of observables in a quantum field theory, quantum theory, is a hard thing. And most often, what we do is compute perturbative expansions. So perturbative computations rely on the existence of some approximation schemes in some small parameter. Typically, this has the interpretation of a coupling constant. And the resulting formal power series here, phi of z, where z is our coupling constant, the small parameter, has typically zero radius of convergence. That means if the an grow as n goes to infinity as n factorial, this is a factorially divergent perturbative expansion. And this is a typical case in quantum theories, and especially in more complicated quantum theories, quantum field theories and string theories. And when this happens, knowledge of the perturbative series by itself is not enough to uniquely determine this original observable that we computing the perturbative expansion of as a function of the coupling constant z. And this is because the divergence of the perturbative expansion is signaling the existence of some non-perturbative terms. And now let me take as a concrete case the free energy of the A-model topological string theory on some Calabi-Yau threefold X. Now this observable is only defined perturbatively by a world genus expansion. So G here is the genus, and the GS is the topological string coupling constant. So you see this is a series in GS to the 2G minus 2. And in particular, if you look at the functional coefficients, the FG are the fixed genus free energies, and they're functions of the scalar parameters in moduli space, the vector T. Now, if you look at these coefficients, they have a common region of convergence in the large radius limit. So when you take this Ti's to infinity, and if you fix the point in moduli space to be in this common region of convergence, and you take now the genus G large, then the functional coefficients, these are now numbers, grow factorially like 2G factorial. And sorry, this should be the genus, not the coupling constant. And in particular, as discussed by Schenker long ago, this signals the existence of some exponentially small corrections in the topological string coupling constant that are hidden in the perturbative expansion. So if we want to obtain an accurate understanding, more complete understanding of the theory, the first step to take is to try to go beyond the limits of classical perturbation theory and try to make sense of these divergences. And one systematic way of doing this, of going beyond classical asymptotics, if the circumstances are good enough, and this can be made mathematically precise, but it is the case in most interesting physical examples, is given by the theory of resurgence developed by French mathematician Jean Nicole in the 80s. The prescription of resurgence is quite simple to describe if we just proceed step by step. So we start with the factorially divergent asymptotic series, phi of z, that I introduced in the previous slide. And now the first step we take is we apply the Borel transform to the asymptotic series. Taking the Borel transform means simply factoring out the factorial growth of the perturbative coefficients. So what we obtain now is a new formal power series, but this is now the germ of an analytic function at the origin in the new formal power formal variable zeta. So it will have some non-zero radius of convergence in the Borel plane. That's the complex zeta plane. However, it will also in general have a complicated pattern of singularities, and we assume this to be labeled by some index omega. So the singularities happen at the points zeta omega. Now, if we take ray in the Borel plane, this rho theta, so this is a ray at angle theta. If we fix it in such a way that the ray does not cross any of the singularities of the Borel transform, then we can compute the Laplace transform of the Borel transform. That's this integral transformation here. And what we're given at the end is the so-called Borel Laplace resummation of the original formal power series along the given ray. And this is a locally analytic function in the original variable z, physically our small coupling constant, that, however, has inherited from the Borel transform the structure of singularities in the sense that this is now only sectorially well-defined, and it has discontinuities at the rays that pass through the singularities of the Borel transform. So this has only sectorial solutions and discontinuities across the so-called Stokes rays. Now, if the Borel transform has a logarithmic type singularity, then one can understand quite a lot about the non-perturbative information encoded in the perturbative expansion by looking at the local behavior of the Borel transform at the singularity. So fix the singular point. If this is a logarithmic branch point, then the local expansion of the Borel transform is given by the logarithmic singular behavior, the log of psi, some perturbative part that I denote in this way to hint at the fact that this is locally analytic at psi equals 0, and so you can think about it as being the Borel transform of some factorially divergent asymptotic series. So a new asymptotic series that's now attached to the singularities, that's this phi of omega. And then in general, one factors out some complex number as omega with a normalization 1/2 pi I. And of course, this number is dependent on the way we normalize the perturbative series. However, whenever one is handed a concrete example, there is a natural way of fixing this. And so we can define what is usually called as the Stokes constant. And then, of course, there's a regular part inside that we're not so interested in. Now, given this, that are like the basic ingredients in the theory of resurgence, what can we understand? So the first thing that one can try to do is, okay, you have your factorially divergent asymptotic series. By taking the Borel-Laplace resummations, you have sectorial solutions in the complex Z-plane. So in each sector, there is going to be a well-defined function of your coupling constant whose asymptotic expansion gives you your original phi. However, as you cross the sectors, as you cross the Stokes rays, and so you go from sector to sector, these functions will be generally different. And so you might wonder how to glue the sector together in order to have a globally defined answer. And so one can, for example, fix a Stokes ray, rho theta, so passing through some singularities, zeta omega of the Borel transform, and then go slightly above, consider rho theta plus, and slightly below, rho theta minus. Take the Borel-Laplace resummations across these two red rays, and then compute the difference between them. This is a discontinuity of the original formal power series. And now if you deform the contour given by these red rays and apply the normal Shinri, then you see that the integral that's encoded in this difference can be computed as the sum of as many terms as there are singularities along the Stokes ray rho theta. So we are summing over omega, where omega labels the singularities with argument theta. And then each singularity gives a very concrete contribution that is the Stokes constant times an exponentially small correction in the formal variable z, whose weight is given by the location of the singularity. And then the Borel-Laplace resummation of the corresponding perturbative series phi omega. Now, if you recall the formula on the previous slide, then you realize that all of the ingredients in the non-perturbative corrections associated to the singularity at zeta omega are already encoded in the local behavior of the Borel transform near that singular point. Now, in very remarkable cases that have been studied recently, there's been a wealth of works in this direction of research. In these notable cases, the Stokes constants that are generally arbitrary complex numbers actually turn out to be rational or even integer numbers. So in these theories, the Stokes constants can also be conjecturally interpreted as enumerative invariants of the corresponding theory, often based on the counting of BPS states. And I list here, so what the examples currently are. There is four-dimensional n equals 2 supersymmetric H theory, complex Chern-Simons theory, and mostly interesting for us today, the topological string theory on toric CUI threefolds. And just to sum up what the main message in this series of works is that in this class of examples, in this class of theories, one has a way of constructing perturbative expansions of observables. And then one can apply resurgence to obtain the collection of non-perturbative corrections that are encoded in the perturbative series. and observe that the Stokes constants that are part of this non-perturbative structure, the resurgent structure, are interpreted as enumerative invariants of the geometry. Now, in this class of examples that I've just mentioned, something interesting happens already at the level of the pattern of singularities in the Borel plane. So in this class of examples where the Stokes constants are rational numbers and they have a enumerative meaning, what is usually observed is some particularly symmetric arrangement of singular points in the Borel plane that have been called the Peacock patterns in the works and complex Chern-Simons theory, and the name kind of stuck in general. So what are Peacock patterns? Basically, when you plot the singularities of the Borel transform, you observe that there's finitely many vertical lines in the Borel plane that I label by this sigma, and sigma goes from 0 to some natural number L, so L plus 1 is the number of vertical lines. And along each vertical line, there is infinitely many singular points that are repeated at integer multiples of some fundamental constant A. This the constant A in the horizontal placement of the vertical lines given by the constant C sigma are dictated by the geometry. So they change example by example. It's not exactly clear how to characterize them explicitly in terms of the perturbative series. So what I try to describe is that the singular points are at the positions zeta sigma m, which are of the form C sigma plus m AI. So m is the integer label that is indexing the singularities along a fixed tower sigma. And what's observed is that if you fix one singularity, zeta sigma m, then the non-perturbative correction that is attached to it has a particular form. So there's going to be a Stokes constant, and this is observed to be rational, as I mentioned, and in some cases even integer. Then there's going to be the exponential corrections that has in the general case is minus e to the minus the position of the singularity over the coupling constant z. And observe here that if you fix the tower sigma, then the weight of each singular point goes like m times the constant A. And then the perturbative part, and this is particularly important, the perturbative part has no dependence on m. So all of the singular points along a fixed tower will have the same perturbative expansion attached to them. The only thing that changes is the exponentially small term e to the minus m ai over z, and the Stokes constant. Also, in all these examples, it's quite natural to organize the Stokes constants along the towers, and so introduce generating series that have this form. So you sum over m s sigma m q to the m. In these examples, this generating series can actually be expressed in closed form as generating functions in the variable q. And as I'll try to describe more concretely in the rest of this talk, these actually play a very important role in understanding this emergent connection between resurgence and arithmetic structures. And let me also end up this section by mentioning that these peacock patterns, so this type of structures in the resurgence of asymptotic series, has been conjectured to appear whenever the theory is governed by some quantum curve. So by the quantization of some algebraic curve in very general terms. So this has been written down in the paper by Jigu and Marcos Marino in 2021. Okay, so if there are no questions about this introduction and motivation part, let me enter into the details of this bridge between resurgence and number theory. And so first of all, let me describe a very apparently simple case, but as you'll see, already very rich, and take the simplest peacock pattern that you can imagine. So you have one tower and place it along the imaginary axis. Okay, so you have Algebraic asymptotic series phi of z. Let me remind you, an are the perturbative coefficients, and z is our small coupling constant. Compute the Borel transform as prescribed by Resurgence, and you determine what the singularities are in the complex zeta plane. And you observe this ray along the imaginary axis, where the singularities are the point zeta m. That's m times some positive real a times I for all non-zero integers m, where a is now fixed. And look at the expansion of your Borel transform at each singular point. Assume this is of the form, so if you expand the Borel transform at the point zeta m, this is minus Sm over 2 pi I psi. So you're taking the case of simple poles, and then there is a regular part. So in the case of simple poles, all of the non-perturbative information is encoded in this Stokes constants Sm. The resurgent structure is indeed reduced to them. And this will in general be complex numbers. So all of the phi m are equal to 1. Now, the very first interesting observation that one can make in this simple example is that if you compute the large order behavior of the perturbative coefficients, so how these an go as n grows, you can actually write down an exact formula. So the an for every n are given by some gamma factor, gamma of n over 2 pi I, and then this series that is summing over m all of the Stokes constants over the position of the singularity to the index n of the perturbative coefficient. So what this is telling you is that in this particular example of a tower of simple poles in the Borel plane, the perturbative coefficients are given by the Dirichlet series, whose coefficients are the Stokes constants, evaluated at all the integer points n. And this is the very first time we see such an explicit connection between perturbation theory and resurgence and some arithmetic structures appearing. Now, this observation is at the beginning of a more general research program trying to formalize this connection and generalize it as much as possible. And so let me first start giving you a definition. And this has been proposed by me and my collaborator Veronica Fantini in our paper from April last year. So the definition is the following. Take a Algebraic asymptotic series, G tilde, so complex perturbative coefficients and formal variable Z. So we call this a modular resurgent series if the Borel transform of this asymptotic series has a tower of singular points at zeta m, where m is where zeta m is m times some constant. So we have this simplest peacock pattern where the singularities are repeated at integer multiples of a along the imaginary axis, and assume that the resurgent series at zeta m are all trivial. So all of the non-perturbative information is contained in the Stokes constants. Let me call the Stokes constants AM now, and hopefully it will be clear why I need to use the slightly different notation. So AM are the Stokes constants associated to these singular points. So I want the Stokes constants AM to be the coefficients of two L functions. So when I plug them into the corresponding Dirichlet series, so for the positive and for the negative indexes. So this Dirichlet series has to satisfy the defining properties of L functions. So they have to possess an Euler product expansion indexed by the prime numbers. They have to converge in some right plane of the complex numbers in the variable S. And the L function is the meromorphic continuation. So I assume that this exists. The meromorphic continuation to the negative alpha plane in the complex S variable. So this is a definition. So nothing much happening here, but I will try to admit that these objects are actually very interesting to study, and they appear in some physically relevant examples. So first of all, the first observation to make is that this modular resurgent series, that, as you can see, they're kind of characterized in a way by the L functions that appear in the definition, so by the Stokes constants, are also equivalently characterized by the Q series that generate the Stokes constant. So one can just repackage the same information into a slightly different form. And given this collection of complex numbers, instead of constructing Dirichlet series out of them, we construct Q series. And so we'll have 2 for imaginary part of Z greater than 0 or smaller than 0. And I take Q to be e to the 2 pi I Z. Then this Q series will be defined in the old complex Z plane minus the real axis. And why is this equivalent? Because there is a canonical correspondence between the L functions, f plus minus, and the 2 Q series that I plugged together into f. That if you want the restrictions of f to the upper and lower alpha planes. So this f restricted to h plus minus. This is the canonical correspondence that goes by means of the Mellin transform and its inverse. So this is effectively the same thing. Now, in the definition, I do not care about where this asymptotic series comes from. So I am just given an asymptotic series. If these 2 properties are satisfied, I call it modular resurgent. But then in all cases of interest, this asymptotic series is given by asymptotically expanding a Q series. Let me call it G of Z. So the tilde is just a signal that it's asymptotic expansion. And so this Q series will be of the same form as f of Z here. But now with different coefficients. Instead of the AMs, let me call the coefficients BM, just some complex numbers. I have no restrictions on them. So the starting point here is I have a Q series G of Z with coefficients given by the numbers Bm. I take the asymptotic expansion and observe that G tilde is modular resurgent. Then what can we say? So for the purpose of being concrete here, I'm going to take some simplifying assumptions, but one can relax them. So let me assume just simple poles and restrict G of Z and F of Z to the upper half plane. So the notation is a bit simpler. And let me now take the Q series F that, so after restricting to the upper half plane is only given by that sum here, sum over m positive of am e to the 2 pi I m z. So these am are the Stokes constants of G tilde. Now, this can be itself asymptotically expanded as z goes to 0 to produce a new formal power series F tilde of z with some perturbative coefficients an. Then one can see that, one can prove that this new asymptotic series is actually modular resurgent itself. So it satisfies the two defining properties of modular resurgent series, and in particular, its Stokes constants can be encoded in an L function G of S and are given by exactly those complex numbers Bm that give the Q series G that we started with. And something very interesting you can see already at the level of this argument, because first of all, since the ANs are defined by perturbatively expanding this f of z here, so you take this formula, you expand and z goes to 0, so you're expanding the exponential basically, and you're switching the sums. Then you see that each AM is given by the L function L in the integer minus n. At the same time, because this is a modular resurgent series, oh, sorry, this L should be an F, capital F, sorry. At the same time, because this AN are modular resurgent series, then they are given by that formula that I showed in the tower of simple poles example. So they are given up to a gamma prefactor by the corresponding L function of Stokes constants at the integer n. So this formula here is saying that the two L functions that are constructed by taking the coefficients of the Q series and the coefficients and the Stokes constants of its asymptotic expansion are actually related to each other via analytic continuation. So this formula is, in a sense, the restriction to integers of the functional equation that's satisfied by a pair of L functions. And this is to signal the fact that, so one can actually prove a general statement that modular resurgent series that come from expanding Q series actually come in pairs, because one can follow this construction that I've described and the loop closes, and the two L functions are connected by a functional equation, and the two modular resurgent series in the pair are such that one equals the asymptotic expansion of this continuity of the other. And why is this true? Because if you look at the commutative diagram here, so this is schematic view over this theorem, but each arrow is an exact proven statement. So let me try to explain this this sentence here. So we started with this Q series G, and then we asymptotically expand it and you obtain G tilde, which is a modular resurgent series. And so it has associated some L function f of s. Then you apply the inverse Melling transform and you get this new Q series. But the AM, which are the Stokes constants of this asymptotic expansion, G tilde, are also all the non-perturbative information that there is. And in particular, if you take the right change variable here, then this series can be identified with the discontinuity of G tilde. So this is equal to the discontinuity of G tilde after one performs a suitable change variable. Because if you remember the discontinuity formula that I showed in the introduction, then there is Stokes constant times exponential, so the AM times the QM times the perturbative part. But in this modular resurgent series, the perturbative part is not there. It's trivially 1. So these are the discontinuities. And if you proceed with the argument, you do the same, then you obtain also that your Q series G is the discontinuity of the other asymptotic series F tilde. And this GS and F of S L functions are connected via a functional equation. Now, this is a purely abstract mathematical statement that holds in this example of modular resurgent series. But something that I find very interesting about these structures is that when they appear in physically relevant cases, then this modular resurgence paradigm is realized in the form of a strong weak symmetry. So I'll give an explicit example shortly. So to conclude this general overview on modular resurgent series, let me mention a connection to quantum modularity. So modular resurgent series have a very rich arithmetic structure where you see Q series and L functions talking to each other in a mathematically precise way. But there is one last ingredient. That is, this series also have very interesting quantum modularity properties. So in particular, let me recall a definition given by Zagier in 2020. So if you take any function defined holomorphic in the upper half plane, say there is a weight alpha, so some integer or alpha integer, and the subgroup gamma in SL2Z, such that if you take this H gamma F of Z for every element gamma in the subgroup, so you fix an element gamma with these entries in your subgroup, and you take the difference between F and this object here. So F, here you evaluate at gamma applied to Z, and then you multiply it by some prefactor dependent on the weight. So this difference here is exactly what would be 0 if this F was a modular form. So we don't want this to be 0 because we're not interested in modular forms, but we want to have a handle on this failure of modularity. So we don't want the failure of modularity to be arbitrary, but controlled in a specific way. So we want this difference to be holomorphic in a much bigger domain than the function f. And in particular, in this definition by Zagier, we define it to be holomorphic in the cut plane C gamma. So this is the all complex plane minus the ray that starts from minus d over c and goes to minus infinity. And so this is indeed a much larger domain only the upper half plane. So when this definition is holding, then we call F a holomorphic quantum modular form. And the conjecture here, fortunately still a conjecture, is that if you have a Q series whose asymptotic expansion is a modular resurgent series, then the Q series you started with is holomorphic quantum modular, is a holomorphic quantum modular form of some weight and for some subgroup of SL2 set that we are not able to specify at this point. So this conjecture is based on observations in many examples. A large class of examples comes from the spectral theory of local weighted projective spaces, and I'll talk about local P2 in detail. But there's more evidence from the theory of mass-cast forms, Q hypergeometric series, and combinatorics, and quantum invariance of knots and tree manifolds.
Okay. Claudia, quick, yes, Claudia, can you hear me? Hello?
Yes.
Hi, yeah, it's Chuck.
Hi.
Yeah, quick question. So the converse to the conjecture, is that known?
No, the converse of the conjecture is not true.
Okay.
So if you have a holomorphic quantum modular form, then the asymptotic expansion is not necessarily modular resurgent. So in a way, the modular resurgent property is stricter. And we're actually trying to understand which subclass of holomorphic quantum modular forms would correspond to modular resurgent series, but it's not known at the moment.
Got it. Thank you.
Okay, good. Yes, so there's a lot of work in progress actually in trying to understand these structures, both from the point of view of physical applications and from the point of view of like pure, mathematical realizations of this. Okay, so now it's the time that I take everything I have said so far and I apply it to topological strings. So let me be quick in just introducing the main object I will apply modular resurgence to, that are these fermionic spectral traces introduced in the context of the topological string spectral theory correspondence. So what are they? Take a toric CY threefold X. You know by mirror symmetry, there's going to be a family of algebraic equations, this OJ of e to the x, e to the y plus kappa j equals 0. So j goes from 1 to the genus G sigma. X and y are complex variables. And this describes a Riemann surface sigma of genus G sigma in C star times C star. The kappa j are the complex deformation parameters of the mirror x hat of your toric CY. And so this encodes the B model topological string theory on the mirror. Now, as proposed in this, in this first two papers here by Marcus Marini and collaborators, if you apply value quantization to the mirror curve sigma, so just take this piece OJ and you apply quantization, you obtain a quantum operator for every j, so OJ of e to the x, e to the y, where now x and y are canonically conjugated Heisenberg operators, so they satisfy the usual commutation relation. So if you take the inverse of this quantum operator, so you define the rho j's to be the inverse of the OJs, these inverted quantum operators have very nice properties. if you think of them as acting on L to R, then they turn out to be positive definite, so they have a discrete spectrum, and all of their traces are finite, so you can compute all of them. So this is conjectured in general, but in all examples of interest is actually proven. And so one can take this collection of operators, rho J, and compute the so-called generalized Fredholm determinant. And this is a function that you see here, the capital Xi of kappa, Xi, and H bar. Xi, the small Xi vector, is just a vector of mass parameters of the Cy. H bar is the Planck constant that is introduced in the quantization procedure. So this Fredholm determinant is entire in the moduli space that's parameterized by the kappa j's. And so you can expand it at kappa equals 0. And the coefficients in this expansion are called fermionic spectral traces. So they are functions of H bar. They retain the dependence on the mass parameters, but it's not important. And they have now dependence on a vector of integers nj, while they're not, of course, dependent on the moduli space anymore. Now, why are these fermionic spectral traces particularly interesting from the point of view of the topological string? What I've said is a construction that only needs toric Cy threefold in input, no topological string free energies involved. However, it turns out that there is a connection that is still conjectural, but particularly powerful. So it's this conjectural spectral theory correspondence that states that the fermionic spectral traces are given by some integral transform, some generalized Fourier transform applied to the exponential of some quantity j. This function is the total ground potential of the A-model topological string on the Calabi-Yau. So you can think of this as the sum of two contributions. The worldsheet part encodes the standard topological string free energies, and the WKV part encodes the Nekrasov-Shadashvili topological string free energies. And in a way, you can think of these two contributions as one being the non-perturbative correction of the other in the appropriate regimes. Let me also mention that in this picture, the topological string coupling constant and the Planck constant H bar are related in this way. So actually the TSST is some sort of strong weak coupling duality between the topological string and the quantum mechanical problem associated with the quantization of the mirror curve. Now, in concrete examples, it's observed and conjectured in general in these papers that if you now fix n and look at the logarithms of the fermionic spectral traces for fixed n, take the limits h bar to 0 and h bar to infinity, you have two families of asymptotic series, then these produce Peacock patterns in the Borel plane with rational Stokes constants. So the picture that I described in the beginning of my talk applies to this physical case. So in the rest of the talk, I'll just try to make everything more concrete by looking at the details of the very simplest toric Cy threefold, that's local P2. So let's see how everything is realized in this case. Local P2 is the total space of the canonical bundle over P2. So there's one complex modulus kappa, the mirror curve is genus 1. It has this form. There are no mass parameters. And you quantize it and you obtain the quantum operator O, that's e to the x plus e to the y plus e to the minus x minus y. And now you take the inverse operator. This is proven to be positive definite and of trace class in the paper by Kashayev and Marino in 2015. And interestingly, the case of local P2, in the case of local P2, the spectral trace, that is the fermionic spectral trace with capital N equals to 1, that's just a trace of the operator rho, is known exactly in closed form and factorizes into the product of a holomorphic block, that's this quotient of cube Kammer symbols, and an anti-holomorphic block, that's the quotient of two Q tilde Kammer symbols, where now Q and Q tilde are given by the usual formula in terms of b squared, and b squared is simply proportional to h bar. So Q is e to the 2 pi I b squared, Q tilde is e to the minus 2 pi I over b squared. W is just a constant. Now, because the trace is known in this very nice closed form in terms of cube Kammer symbols, then it's possible to obtain the perturbative expansions of the logarithm of the trace for both h bar going to 0 and inverse of h bar tau going to 0 at all orders in perturbation theory and exactly. So one can compute the asymptotic series, phi of h bar and psi of tau, and the perturbative coefficients are known in closed form for every order. And then the statement is one can prove that these asymptotic series are modular resurgent series. And moreover, they are a canonical pair of modular resurgent series. So they satisfy that commutative diagram that I presented in general. So you have two towers of simple poles. The purple is the weak coupling limit, and the blue is a strong coupling limit in h bar. And the Stokes constants Sm and Rm are given by particularly simple arithmetic functions. They're just divisor sum functions, where now there is some very evident symmetry between the two regimes, as in this formula, you see the only thing that changes is the factor multiplying the Dirichlet character chi3. And in particular, you go from one to the other by changing d with the dual divisor m over d. So chi32 is the Dirichlet character modulo tree that associates an integer with its class, congruence class modulo tree 0, 1, and -1. And so these are rational numbers, but you can see that if you take the Stokes constant normalized and you multiply it by the index m, in both cases, what you obtain is a sequence of integer numbers. So this number that I plot here next to the singularities, and these are quite remarkable sequences of integers. Indeed, you can see that if you plug them inside their Dirichlet series, then the corresponding objects L0 of S and L infinity of S are actually L functions, as is required to be modular resurgent series. But some interesting additional observation is that these L functions factorize as the product of the Dirichlet L function associated to the character and the Riemann zeta function. So the factors are the same in the two regimes. The only thing that changes is that there is a shift in the arguments between the two factors. There's this crossed shift S into S plus 1. Now, this is particularly important because it allows us to prove that Actually, if you complete these L functions as one would normally do in analytic number theory, then their completions satisfy a combined functional equation. Lambda 0 is equal to lambda 0 to S is equal to lambda infinity minus S. And moreover, if you take the discontinuities of the two series, these are given by the Q series generating the Stokes constant. These are given by the same Q tilde Q blocks that appear in the factorization of the spectral trace. And if you expand it, you get the opposite asymptotic expansion. So each of the two functions, each of the two blocks, gives the perturbative data in one regime and the non-perturbative in the other. And so if you put everything together, this is just the same commutative diagram that I showed in the case of modular resurgence in general, but I wanted to show it again here to make it clear how in this physical example, modular resurgence realizes as a strong weak coupling symmetry. And it is an exact symmetry, not just a coupling duality. And this can be also interpreted in terms of the S-type duality between the two parts that enter the total ground potential of the topological strings, but it's more of an intuitive statement for now. So let me conclude by saying that, of course, also in this case, the conjecture is verified. So this modular resurgence series come from expanding the generating series of the Stokes constants that correspond to the discontinuities. And this F0 and F infinity are holomorphic quantum modular forms. In this case, the weight is 0. And the group is the congruent subgroup gamma 1, 3. And also, if you take the Fricke duals, these are also holomorphic quantum modular forms of weight 0 for the same group. Now, there is a series of observations that one can make, but as I'm short of time, I just want to say that this group, gamma 1, 3, is very closely related to the symmetries of the moduli space of local P2. And it is not entirely surprising that this quantum modularity for this subgroup appears at the level of the resurgent structure as well. So let me conclude with a brief summary. So how this allows us to access the non-perturbative sectors of given asymptotic series. And mathematically, this means producing new formal power series with an exponentially small dependence on the coupling constant. Now, in remarkable examples, the non-perturbative data that one obtains by applying resurgence has some number-theoretic structures encoded in it. And these structures reflect symmetries of the geometry. So there's this connection that is emergent in this area of research and still to be fully understood. But the framework of modular resurgence is a way of taking the first step to formalizing this observation. And let me mention that there is more things that one can say, connections to the BPS invariance of local P2 in this case, and studies on the periods. Maybe one last remark I want to make is that this strong weak resurgent symmetry for local P2 generalizes. A version of this generalizes to all local weighted reactive spaces. And this is something that should appear on the arXiv very soon. And I'll stop here. Thank you very much.
Do you have any questions from Zoom? speaking.
Yeah, so could I ask one? Can you hear me?
Yes, I think.
Okay, great. Wonderful.
Yes.
Yeah, so my question has to do with going up a dimension. So you mentioned the sort of natural observation that the gamma 1 of 3 that's showing up here ought to be related to the natural modular group for, say, anticanonical cubic curves or anticanonical elliptic curves in the P2, right? Because it's a local P2 model. And this, of course, shows up naturally in mirror symmetric constructions and whatnot. But now let's just play this game. Let's go up a dimension. So now we're working with, let's say, P3. So we're talking about quartic K3 surfaces as the anticanonicals. And if we expect the group to be related, say, to the mirror, well, then this would be the quartic mirror K3 family. Now, the quartic mirror K3 family does have a relationship to a certain kind of modularity in its moduli space. There's a modular curve, but it's not a quotient by a subgroup of SL2Z. Now you actually have a Fricke involution taking you into SL2R, but not SL2Z. Okay. Strictly speaking, if you want integral monodromy matrices, you're working with a symmetric square, but it's okay. If you want to make the connection to modularity, you can take the symmetric square root. But it's at a cost, and the cost is that you're no longer in SL2Z. So what I'm wondering is whether the notion of quantum modularity, which is at the heart of the first portion of your talk, maybe needs to be weakened, and maybe it's going beyond Algebraic 1, or maybe it just needs to be weakened to allow for what we expect would be a more general phenomenon, even for local P3.
Yeah, that is possible. I guess that's up for discussion, because we're thinking about this, and it's very interesting observation. I think it is possible that it is what you say. It is, as I pointed out at the beginning, the collection of quantum modular forms, these holomorphic quantum modular forms of Zagier, is not the right group of quantum modular forms per se. It's not exactly the right group. So in these examples, all the quantum modular forms satisfy this definition. But yes, as we study more examples, it's possible that we might go beyond that, and that would be very interesting to see. I think we should talk about this.
Absolutely, we'll be talking a lot in the next few days. As one goes up that tower of projective spaces, even to higher dimensions, you'll lose even that kind of modularity in the moduli space of the mirror anticanonical Calabi-Yaus. So it'll be interesting to see how the resurgent series approach is or is not taking this into account, or maybe there's subtlety having to do with what the enumerative problem is as you go up dimension.
Yeah, so I think I lost the first part of your sentence. I think also people need the room.
Oh, okay,
so
we'll let them go.
Yeah.
Okay, thank you so much, Claudia.
Of course, thank you, and we'll talk more about this.
Okay. We just have a request to show the last slide.
Show the last slide.
Okay. Or that's fine. Okay, so that's thanks, speaker again. And